right. So, okay. All right, there we go. So what I want to do today is to basically continue where we left off last time. We were looking at all of these properties of tensors, um, and we'll talk about um, change of coordinate systems today, and a couple more interesting properties of tensors, which are called invariants. So let's see how much we're able to cover today. Any particular questions from what we've been talking about in terms of tensors itself? I know it'll take maybe some time for you to get accustomed to what tensors are and how to use them and all that. But very quickly to kind of review, let me ask you this. What is a tensor?
The quantity that acts on a vector to give another vector.
Right. So the best definition of a tensor is that essentially it's a physical quantity, something like stress or strain, that acts on a set of vectors to give you another set of vectors. So think of that red sphere of arbitrary vectors, and when tensor acts on that red sphere, it takes you to a blue ellipsoid of mapped vectors, right? And indeed, that's how we defined it. And what exactly a tensor does, the shape of that tensor, the shape of the resulting ellipsoid is basically what defines a particular tensor. A different tensor might give you a different ellipsoid, but they all take the original same set of arbitrary unit vectors. Okay. All right. So in terms of properties, we were looking at all of these properties, linearity, how they can be added and subtracted. Um, we introduced this dyadic product last time of how you would construct a tensor using two vectors. And we saw that something called a tensor basis last time, just like we have a basis set of three basis vectors to define a vector v1, v2, v3. In the same way, tensors have these 9 basis vectors, which are denoted by EI, dyad, EJ. So when you list all of those 9 possible uh, tensor basis, you get these 9 different tensors which correspond to specific positions in the component matrix version of that tensor. Okay. So essentially, any tensor can be written in terms of its 9 component uh, component tensors, which are given in those individual tensor bases. And we saw that the way that a tensor acts on a vector can also be done, can also be represented in terms of components, where this entire thing was the tensor. This is the tensor expressed in its tensor basis. This is the vector expressed in its vector basis. And when we multiply all of this out, we saw that what we are essentially doing is something like this, that we get Tij, Uj, and note that j is repeated, so there is a sum on the j, and the fact that that when j is repeated like this, it essentially means that we are taking a 3 cross 3 matrix and acting it, this is a 3 cross 3 matrix acting on a 3 cross 1 vector to give me a 3 cross 1 vector. And when we take those components and multiply it with the basis vectors E, we get the resulting vector, which I'll write simply as V. So the vector V is equal to tensor acting on U, which is equal to these components in the direction of EI. Okay. By the way, can I write equal to here? This is a vector, tensor acting on a vector is a vector, but is this a vector? It is indeed a vector, even though there are indices in there. Those indices are being multiplied with the basis vector to give you finally a vector V. So the equal to sign is correct here. We looked at these examples of tensors, and about last time where we were was this composition of tensors. So I was telling you that you can compose 2 or more tensors to come up with a new tensor, which essentially would be like combining those ellipsoids to get a new ellipsoid, right? So we looked at this, how that works. if I have two tensors S and T, I could be composing them to come up with a tensor R. And in terms of components, what that means is that I would take tensor T, act it on U first. Whatever I get would be a vector. Then this tensor acts on that resulting vector to give me yet another vector. And we went through all of this calculation to finally see that the vector that we get is this long expression. So let me ask you this. In this parenthesis expression out here, um, in this parenthesis expression, what is, how many indices are repeated, first of all? Are three repeated or two repeated? Which ones? Those are J and L. J and L are the repeated indices. J repeats here, L repeats here. I is the free index. So indeed, the result of all of this would be three possible values, because for I equal to 1, I will get one value, which would be a sum of 9 terms. For I equal to 2, I would get again another value, which would be again a sum of 9 terms, and 3, sum of 9 terms. For each value of I am multiplying it with E1, E2, and E3, and that would result in the vector V that we originally wanted. Okay. The key thing that I wanted to show you last time here was that this product right here, Sij TJL, if you remember what we were doing last time, we set that Sij TJL is like the matrix multiplication of, let's say, those 9 terms here, 9 terms here, and the result of all of that is what? The free indices would be I and L. So indeed, those would be on the left-hand side. And since we are calling it R, so RIL is equal to Sij TJL. I'll show you one example, and then I'm sure you'll get what this is doing really. So let me pick that I want to find R2, 3, correct? Second row, third column. If I want to find R2, 3, what I would be doing is I would substitute 2 in place of I, 3 in place of L, and I note that J is being repeated. So that means I need to sum over 3 terms of J. What would be those 3 terms of J? For going from 1, 2, and 3, which would be go to the second row here, 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 and the third column, this, and multiply these 3 numbers with these 3 corresponding numbers and add them together. Right? That's exactly what this operation means. Sij TJL, and since J is repeated, there is a sum here, J going from 1 to 3. And that gives me the value R23. So in the same way, you can think of any other possible combination in that resulting matrix, R11, R22, R33, or R32, whatever. In the same way, you will get all of these different 9 possible values, because this expression has 2 free indices, I and L, which means 9 independent values, and 1 repeated index on the right hand side, J, which means for each value I would have a sum of 3 terms. Make sense? So you need to start recognizing these types of expressions where I say Sij, and the second index of S and the first index of T is repeated. So that immediately should click with you that this is matrix multiplication. In the exact same way that we had on the previous page, you see Tij, second index of T, first index of U, well, the only index of U, they are repeated, which immediately means matrix vector multiplication. So in the same way we have Sij, Tjl, that's matrix multiplication. So we need to start recognizing these types of expressions. And finally, I'll write, I'll try to express what Ri what the tensor R might look like. So we defined R as S composed with T. And if you see here, when I'm writing S composed with T, I have SIK EI dyad EK. Okay? And then TLJ EL dyad EJ. First question. On the right hand side of this expression, any free indices? No free indices. Any repeated indices? How many? How many? Four repeated indices, right? I, J, K, and L, which means how many terms? 81 terms. It's a sum of 81 terms. Why? Because there are 9 components in S, 9 components in T, 9 times 9 is 81 terms, which is basically what you'd be doing if you were multiplying two 9 cross 9, 3 cross 3 matrices, right? So, so indeed, if we write all of that matrix times a matrix operation, you are doing multiplication 81 times, and a good shorthand way of writing that is right here. So we know that um, when we multiply or when a tensor acts on a vector, here actually a tensor is composing with another tensor, but the same type of operation works in this case as well. We will take the second basis vector here and the first basis vector here and do a dot product between them to get ek dot el, which is delta kl. Okay. And what will be remaining would be ei dyad with ej. So that's what's remaining here. And delta kl comes here. Finally, we'll contract out some of the components. So one way to do that would be to cross out this L and this L and replace that with K. Okay, so what I get then is SIKTKJ, which is all written here on the last line. And once again, this thing out here is RIJ. So what I have then is that the tensor R is written as Rij Ei dyad Ej. That's just listing out the 9 components of that tensor R, where each of those 9 components are obtained by a matrix multiplication of the components of S and T. Okay. That's what tensor composition is, and essentially in terms of components, we are representing that with matrix multiplication. So a lot of these properties of tensors you'll see are very similar to properties of matrices that you already know. But tensor is not a matrix. Tensor can be represented with a matrix if you fix a particular coordinate system. In a different coordinate system, you get 9 different components of the tensor, right? So the same difference that we have between vectors in 2 different coordinate systems also holds for tensors in 2 different coordinate systems. Okay, lot to process here. Okay, let's see. Couple of special types of tensors. If I have a tensor T, I can create a tensor inverse. How? As you might imagine, if a tensor T takes an arbitrary set of vectors u to a new set of vectors v, then the inverse tensor will take the resulting v vectors back to its original u vectors. No surprise there. And any guesses on how you can get the components of the tensor inverse? Inverse matrix, right? If you know the components of tensor T, you just invert the matrix, and that would be the components of the tensor inverse. No surprises there. The tensor transpose, that's sort of a weird concept, but it is defined in this way. You know how we have a matrix, and to get a transpose of a matrix, what do? Okay, so we interchange the rows and the columns. Essentially, the diagonal remains the same, but you flip the matrix. Anything horizontal vector becomes a vertical vector, and so on. That's how we used to do matrix transposes. But the way a matrix transpose is defined, or even a tensor transpose is defined, it's defined in this manner. See these three equal to lines? This means defined. So the idea is that given a tensor T, pick any two arbitrary vectors, u and w, could be anything. And as long as I compute T acting on u, I'll get some vector. Dot product of that vector with the vector w, which is also arbitrary, should be equal to, now if I switch the u and w, on the right hand side I have tensor, some transpose tensor acting on w and dot product with u. So if this equation holds, then T and T transpose, of course, are then T transpose would be the transpose of this tensor. This is how it is defined. Okay. Of course, in matrices or in components, the consequence is that if you flip the rows and columns of a tensor, you get its transpose tensor. The physical interpretation is a bit messy. It's not really very good. There's not a good physical interpretation for this transpose, but I'll give it a shot here. So the idea again is a set of arbitrary vectors, pick up one arbitrary vector u, tensor T acts on it, takes you to Tu, and this resulting vector Tu is going to get dot product with another arbitrary vector W, and what you're going to get is a scalar, right? So the dot product of these two vectors would be a scalar. The idea of a transpose is that you take this arbitrary vector in the original space, act the transpose tensor on it, you get some other vector T transpose acting on mu, and then dot product that with the original u, and the two scalars that you get in this case should be the same. Okay, so that's how a transpose is defined, and I'll show you now how to get a transpose of a tensor in terms of its components, and we'll see that exactly why we have to exchange the rows and columns for that. So what I'm doing here is just writing the same expression in terms of indicial notation. W becomes WI, T becomes T, or T acting on U becomes TJK, K is repeated with U, so that's a matrix vector multiplication right there. And the result should be in the direction J, EJ. That's why T acting on U is written as this, T acting on U in the direction EJ. All of that is just a component notation. EI dot with EJ gives me delta IJ, contract J out, I get this expression, UK WI TIK. On the right hand side, I'll do the same thing. U gets, this is the definition of the vector U. T transpose could be some tensor. I'm going to write it as NL, WL, and EN. Do you agree? I hope that on the right hand side, I've just written out a component version of that operation. So any guesses what should I do next? How can I simplify this expression? Yes, so first I need to do, I need to have a delta in here, which means that, of course, if I take EM and EN dotted with each other, should give me delta MN. I'll write that out. I get UM T transpose NL WL delta MN. I'll contract out, let's say, okay, we can contract out anything, but let's contract out N. So I'll replace N with a M here. And what I get then is UM T transpose ML WL, no E's or nothing, right? Now, question is this expression similar to this expression? On the left hand side and the right hand side, I have this expression and this expression. Are they similar or even same? How can we judge? We are using different indices. indices are all repeated here, right? So they are dummy indices. I can replace them with whatever I want. So I'll do that. To match the expression on the left, I'm going to replace M with K, and I'm going to replace L with I, and I'm going to replace, is there anything else in here? Well, the only thing. Yep, so that's the only thing. So if I do that, I get UK T transpose KI and WI, right? So I can see that UK matches WI is there, and what I'm left with is TIK versus T transpose KI. That immediately means this expression right here that I've written, that TIK is transpose um, the components of T are the transpose of the components of T transpose. No surprises there, right? So you should be able to see that this is equal to this, which is what I've listed out here. That's why taking a transpose means switching the rows and columns. It's not the other way around. You define the tensor transpose first, and the fact that tensor transpose means you switch the components gives you the property of the matrix transpose. Kaiju.
I have a question that when I go about to the inverse, and we know that in matrix there's sometimes the inverse matrix does not exist.
Correct.
So I think maybe it's the same to the tensor.
That's
so
true. Yeah, there are degenerate cases. We'll come to that actually. There are degenerate cases. So the question is, sometimes matrix inverses don't exist. That's absolutely true. Why? Because the matrix sometimes is singular. So that the fact that a matrix is singular is also sometimes represented by special degenerate vectors. And one example of that is something that I probably gave you last time, projection tensor, right? In the projection tensor, you don't get an ellipsoid. You actually get a flat ellipse, which means that if you try to invert it, there's if you pick up one particular vector from a flat ellipse and try to go back to or try to find its original vector it came from, there are multiple possible original vectors. That's a singularity. So indeed, a tensor inverse does not always exist. That's true. Okay, good point. All right. Couple other properties of these tensors. Symmetric tensors. As you might imagine, they are related to symmetric matrices. But the idea is that anytime a transpose of a tensor is the same as the tensor, we get a symmetric tensor. So we'll use the definition of a transpose. This was the definition of the transpose. If I use that definition and it so happens that the tensor here is also its own transpose, I get a symmetric tensor. Okay. Skew symmetric tensors, if the tensor here can be the same tensor here but with a negative sign, that's the definition of a skew symmetric tensor. So if the product that you get here is negative of the product on the left, then it's defined as a skew symmetric tensor. And no surprises again, a skew symmetric tensor is represented with a skew symmetric matrix, right? And usually we use the symbols S and W for symmetric and skew symmetric tensors. And the property of a skew symmetric tensor, of course, is that if you take the main diagonal, on the off diagonal components would be negative of each other, right? So here's the question: what would be the diagonal entries of a skew symmetric matrix? 0. Indeed, for any skew symmetric matrix, the diagonal entries would be 0 and the off diagonal entries would be negative of each other. For the symmetric tensor, off diagonal entries would be the same. Diagonal entries need not be 0. Okay. And finally, Any tensor can be expressed as a sum of its symmetric and anti-symmetric or skew-symmetric component. You can take any tensor T, break it up into its symmetric and skew-symmetric part. So these are useful properties to know, because later on we'll use those properties of skew-symmetric and symmetric tensors to deal with stress and strain. Why? Because stress and strain are symmetric tensors, right? So a lot of times we'll use these types of properties. Questions, Viri?
Yeah, I would like to know like the whole transpose definition, like where is it used in?
When is it used?
Yeah,
Yeah.
I mean, like, why do we do it?
So yeah, there's lots of times that you have to use a tensor transpose, as we'll see later on when we are looking at deformations, that will come in chapter 2. Your strain tensor, the strain tensor is defined by taking what is called a deformation tensor and multiplying it with its own transpose. And there is a reason for that, because you want to remove rigid body modes, and we'll come to all that. So yes, there's very good reasons to understand what is a transpose and how it is used. So we'll use it later when we are defining deformations.
I mean, it came the other way around, like from the deformation strain relation, this definition.
Right. So that's kind of a funny way of how physics and mechanics really works. When physicists and mechanicians observe something, they try to build up the math to explain it. So this is some of the math that we'll use later on to try to explain how deformation and how stresses act upon or work with each other. Okay. All right. Um, so that's a brief introduction to tensors. Um, and let me talk a little bit um, about the need for sometimes when you have to change your coordinate system. So I've been harping upon this fact quite a bit, that a tensor is not a matrix, a vector is not a 3x1 set of numbers, right? That these are just ways to express tensors and matrices given a particular coordinate system. So naturally the question arises that if I have one coordinate system and somebody else comes along and they have a different coordinate system, then how do we talk with each other? How can we convert the components of a vector or a tensor given one coordinate system to a different coordinate system? So I would like you to note that this arrow, this is a vector, magnitude and direction, does not depend upon coordinate system. If I pick a coordinate system, it gives me 3 numbers with respect to that particular coordinate system. Exactly the same arrow, but in a different coordinate system gives me 3 different components, right? 3 different components, v prime, v1 prime, v2 prime, v3 prime in a different coordinate system. The question is, how do I convert v1, v2, v3 to v1 prime, v2 prime, v3 prime if I know which way these 2 coordinate systems are pointing, right? I should be able to do that. Since this is the same physical quantity, same underlying physical quantity, I want to know how to convert between each other. So there is an easy way to do it. Anybody know, or has anybody tried this type of a thing in the past?
We can actually find out what are the coordinates of the second system with respect to the first system. Then
Right. So yeah. Yeah, so adding and subtracting accordingly gets a little bit tricky in this case, but we'll talk about that. So I was referring to maybe back in your second or third year, you might have used Mohr circle, right? You had one coordinate system and you rotate it by 45 degrees and you get alternate states of stress and strain. That was the process that we used to use to transform a tensor. Usually in those, back then we were using like X, Y components only, Z became too complicated. But that's how you used to transform the coordinates of or the components of a tensor from one basis system to another. Now, in 3 dimensions, Moore's circle does work, but it gets a lot more messy. So the easiest way I find to do change of coordinates is to use the definition of the vector or a tensor itself. Let's see how we do that. So we said that vector v in this coordinate system can be written as vi ei, and ei has to have an underline. In the other coordinate system, we would be writing the same vector v as vi prime ei prime. Okay. You remember, if I want to get a particular component of a vector, say vi, how can I obtain vi? If I have a vector v and if I want to find its component along E1, what do I do? Right, I dot product it with E1, right? If I want V2, I dot product it with E2 and so on. So to calculate Vi, I'm going to write that as vector V um, um, dot with EI. Okay. So, and the same thing on the right hand side, but in this case, I will dot it with the different with a different basis vector. So we have a v dot with ei prime, and now I'll substitute the expression for v from this right here. Sorry, from this one right here. A vector v, I can write that as vi or vj prime times ej dot with ei. Do you agree with this expression? First of all I did was to expand v in terms of the other basis vectors. Say again. Sorry, yes, ej prime. So I'm expanding v in terms of vj prime ej prime. That's v in the parenthesis, and on the right hand side I just have ei. So same thing I'll do on the right hand side. With the other basis, I'll write it as vj ej. I'm sorry, I also missed a prime here. So that, no, actually I didn't. So this would be ei prime. Okay. And now I can rearrange this expression by just writing it in terms of vj prime and let me write ej prime first. So ej prime dot with ei, and on the right hand side I have vj, and in the brackets I have ei prime dot with ej. So it looks like we are just rearranging terms, and already we have an expression to convert between vi to vj prime or vi prime to vj. And if you look at this quantity in the brackets, this is what we are going to call qji, or on the right hand side it's qij. Q is here it's a matrix. Okay, we have not Q is not a tensor, even though it has these two indices. Q is not a tensor. Q is a matrix, the way that we've defined it here. So Qij is defined as ei prime dot ej. What would that be? It would basically be the product of, or the dot product of, for example, E1 prime with E1. I have these two basis, these two sets of basis vectors. I have one E1, E2, E3. I have another E1 prime, E2 prime, E3 prime, and they are oriented in different directions. So to find these values of qji, what I would have to do is to dot product one of the basis vectors from the prime system with another basis vector from the unprimed system. And how many possible values would I get? 9 possible values, because indeed I could be going from 1 to 3, j could be going from 1 to 3. So we are looking at q11, q12, q13, or q21, and so on, right? Which would all be obtained by just doing a dot product of, for example, e1 prime with e1, e2 prime with possibly e3, and so on. There are 3 vectors here and 3 here, which gives us these 9 different numbers. And these can be represented, or this operation itself can be represented very nicely in the matrix form as I've laid out here. So if you look at this, qji, I can also write that as q transpose ij. Do you agree? qji is nothing but q transpose ij. And qij acting on vj is nothing but this matrix of q transpose acting on the primed components to give me the unprimed components. On the right hand side, for example, if I want to go from, if I know the primed components, for a given vector, I can calculate the unprimed components using the Q transpose matrix. Or if I know the original components, unprimed components v1, v2, v3, I can pre-multiply with this Q matrix to get the primed components. So for example, the problem that I had originally posed up here, that if I know v1, v2, v3, how can I find v1, v1 prime, v2 prime, v3 prime? I can use this expression. I know this because I can do the dot products of all of these vectors with respect to each other. And these will be just a bunch of 9 numbers, and they will give me the components v prime in the new coordinate system. So that's how you would take vectors from one coordinate system to find components of the same vector in a different coordinate system. Doesn't matter how complicated the orientation of this new system is with this old system. I know you might be used to using like a coordinate system in 2D. So if I give you x, y, and if I give you x prime, y prime, you can do that with cosines and sines. That works perfectly fine. But for 3D, when all the 3 axes are in sort of oriented in a general 3-dimensional direction, cosines and sines becomes very complicated, right? So this approach will always work, whether it's 2D or 3D, right? And just to relate it to something that you might know with cosines and sines, let me ask you this. If I had a special case where E3 and E3 prime both are acting out of the plane, pointing towards you, coincident, right? E1 and E2 are pointed in this way, and E2 prime and E1 prime and E2 prime are pointed at a 45-degree angle, let's say. So E3 is coincident, E1 and E2 prime make a 45-degree angle. You would use cosines and sines in that case to figure out how they need to be transformed, right? If that was the case, let me ask you this: what would be what would be E1 prime dot with E1? What would no? So E3 is the same, but E1 is pointing in the x direction, and E1 prime is pointing at 45 degrees. So E1 dot with E1 prime would be cosine 45 degrees, right? That's right, 1 over root 2. But the fact that you use cosines and sines to relate those two types of sets of vectors stems or is derived from the fact that this relationship E1 prime dot with E1 is actually a cosine of that angle, right? So we we were able to simplify back when we learned about all of that. We were able to simplify these expressions to come up with special cases for transforming vectors in 2D using the cosines and sines and trigonometric expressions. But the original general expression, this works for 2D or 3D. Questions on this? So we are basically we just learned about how to transform vectors between one coordinate system to another. And I said that we do that by using this Q matrix. Okay, so that's what this note also says here. Q here is a transformation matrix, not a tensor. And another good property of Q is that this is an orthogonal matrix. Yes. Yeah. So I'm coming to that. Yeah, I'm coming to that. So Q is an orthogonal matrix. Okay, and the property of an orthogonal matrix is that if you take that matrix, multiply it with its transpose, you get the identity matrix. Hopefully you remember that from linear algebra. Q transpose is identity, or Q transpose times Q is also identity. Right? And this helps us quite a bit in a little bit as I'll show you. Now, as the note final line says, you can construct a tensor Q which has same components as this matrix Q, but the physical interpretation of those two things is completely different. Okay, you can construct a tensor Q that will take the basis vectors EI primes to their unprimed basis vectors. What does that tensor do? That tensor Q takes these basis vectors E1 prime, E2 prime, E3 prime, and what does a tensor do when it acts upon a vector? It gives you new vectors. It gives me these black basis tensors when I act that tensor on this set of tensors. It does not create a new ellipsoid. It just takes that sphere of arbitrary vectors, rotates it in 3 dimension, a rigid body rotation, to give me these tensors. So a sphere to a sphere, a rotated sphere. Okay, that is indeed a tensor. But the operation that we talked about, this Q matrix does not do that. A matrix just takes these 3 numbers to a set of different 3 numbers. Okay, so there is this big difference that in one case a tensor is a physical quantity that takes vectors from one. A tensor is a physical quantity that takes a set of vectors to another set of vectors. Whereas the Q matrix that we're talking about doesn't do that. It just takes these 3 numbers to set of different 3 numbers. It just so happens that that if you were to take these components of Q and if you were to express them in terms of or if you use these components to create a tensor Q, then that tensor would take these vectors and rotate them to E1, E2, E3 prime. So that's a subtle but an important difference. Why it's not a matrix? Why it's a matrix and not a tensor? And this problem 13 is in your books, which you will actually get to do on homework 2. Go ahead. Yeah. Mathematically differentiate. Yeah.
Q is again a matrix, right? A tensor that can be defined in terms of matrix.
So a tensor can take these arbitrary set of vectors to these set of vectors. That's a tensor. Okay. I've not talked about components or anything here. It just so happens that if you were to try to calculate the components of that tensor, you would come up with these 9 components. The function of these 9 components that we came up with was to transform these 3 numbers to these 3 numbers. So that's the only important difference between a tensor and the Q tensor and a Q matrix. Okay, but I think once you do problem 13, you would have to recognize this important difference, and Once you do that, I'm sure you'll get a you'll get a better understanding of why we cannot call this matrix as a Q tensor. Uh, so uh, I'll let you figure that out first, and then of course we can discuss more if you have questions. All right. So um, going back to this change of coordinates. Um, I showed you here how you can take a vector and use this Q transformation matrix to get its components in a different basis system. And I've also told you that instead of a vector, if you had a tensor, you would get 9 numbers in this coordinate system. You would get different 9 numbers in this coordinate system. Let's see how we can convert that. So that is what is called a transformation of tensors, and that is what I was referring to when I was talking about Mohr circle being used to transform the stress and strain in 2D. But in 3D, if you have a tensor T in one basis system, E1, E2, E3, I would get Tij components, 9 components. In a different basis system, the primed system, I would get different 9 components. But they're both referring to the same tensor. What tensor? This tensor. This entire thing is a tensor. This tensor can be expressed in one basis system or another basis system. Okay, and let's see how we can do that. I think I might just have enough time to do that, and then we'll call it a day. Um, so we'll use the same type of operation that we did for vectors. We have Tij, so Ei dot with Tij, or actually let me use different indices because, so Tmn Em dyad with En, that's my tensor T, and it's going to be acting on Ej. So the way that a tensor acts on a vector is by taking a dot product of those two, which gives me delta Nj, and what I get is Tmn in the direction delta Nj, and what I'm left with is Ei dot with Em, right? So this Ei will dot with Em because the result of all of this would be delta Nj Em. And indeed, these two put together would be delta Im. And once again, if I contract N with this N, I get J here. And this M and this M, I get I here. So what I get on the right hand side is Tij. No surprises there. All I showed you was that just like for a vector, if we take a vector, dot it with its basis vector E1, we get V1. In the same way, if I take a tensor and pre-dot it with EI and act it upon EJ, I get the Tij component. And but now I'll express the same tensor in a different coordinate system. So I will have EI dot with, say, T prime Mn, Em prime dyad En prime, and acting on Ej. What I get now is Tmn prime, and I get these would be dotted together. First question, is this delta Nj? No, because one is prime, one is not prime, right? So this would be Qnj, correct? So I'll write that as Qnj, and on the left hand side of that operation, I would have this. This would be equal to Qn mi, or I can write that as Q transpose IM. And there is a good reason why I wrote it that way, because the second index of this Q transpose is the same as the first index of this T prime, and the second index of T prime is the same as the first index of this Q, which means what? Matrix multiplication of 1, 2, and 3 matrices. If I take 3 cross 3 matrices and multiply them together, I would get a 1 3 cross 3 matrix, which would be the original Tij. So using this, I have related Tij with Tmn prime. So just like for vectors, we pre-multiply with Q. For tensors, we post-multiply with Q and pre-multiply with Q transpose. Okay. So I'll leave it there, and then we'll discuss more next week. Monday is, of course, a holiday. We'll come back and finish out tensor invariance on Wednesday. Okay. All right. See you all on Wednesday.